All right, this is 5.2 part 2 in Math 31, where we just kind of do more asymptotes. This is, this question, this example, whatever, is really a lead into what we're looking at in chapter 5, which is to look at the equation for a curve, a function, and basically solve, I think it's 6 or 7 headings, and then we can graph that function without technology. And that is an important consideration. If nothing else, this makes you very sharp at graphing functions. So it wants us to find the horizontal and vertical asymptotes. Now, vertical asymptotes are about that limit as x approaches, and I'm just going to put positive, negative NPV there of the function. That's really what you need to remember. And then the horizontal asymptotes are the limit as x approaches positive and negative infinity of the function. And there's a very important consideration. A lot of students get confused because when we have a vertical asymptote, the limit is equal to, often positive infinity or negative infinity for that matter. But when we talk about horizontal asymptotes, it's the limit as x approaches infinity. And that's a really, really crucial distinction, that vertical asymptotes are about the behavior of a function as it approaches an x value. Horizontal asymptotes are about the behavior of the function as it, continues on for infinity in the positive direction or the negative direction. So with that in mind, I'm going to do vertical asymptotes first. So my vertical asymptotes, I'm going to put up here that my NPV is that x cannot be equal to positive 2, because that would make the denominator of my function equal to 0. To really, really kind of, determine exactly what's happening here, we have to take the limit as x approaches 2 from the positive of our function, and maybe I won't write the function, I'll put the actual function in there, which is, and I put this positive negative on the wrong side here. Sorry, guys. That's the left and the right-hand limit of the NPV there. And this function in this question is x plus 1 over x minus 2. Now, we're going to use the same technique we talked about in 5.1. As we approach 2 from the positive side, we're talking about maybe 2.1. That means that the top of this fraction will be positive, 2.1 plus 1. The bottom of the fraction, because we're approaching 2 from the right-hand side, x is slightly larger than 2. So when I subtract 2 from that, what I get is a very, very small positive value. And if I take a positive number divided by a very, very small positive number, what I get is positive infinity. Now, this lets me know that as the function approaches that vertical asymptote, it will veer upwards or approach positive infinity. We do have to consider both sides, though. So we'll take the limit as x approaches 2 from the negative or the left, which is still the same function, x plus 1 over x minus 2. The top would still be positive, but now the bottom would be a very, very small negative value, and therefore it approaches negative infinity, which means the graph veers downwards near that non-permissible value. Okay, half done. Those are my vertical asymptotes. Now, for this particular question, the horizontal asymptote actually isn't going to matter if we approach positive infinity or negative infinity. I'm going to talk about how I know if that's true. So to find my horizontal asymptotes, I'll put an HA right there. I'm going to take the limit as x approaches infinity. I like to start with positive infinity first of x plus 1 over x minus 2. But this is an infinite limit. So what I have to do is I have to manipulate the inside of that limit by multiplying by 1 over the highest degree in the numerator and denominator. Very importantly, that because I'm multiplying by this entire, red bracket there, I want to write that this is equivalent to 1, and therefore I can get away with doing it anywhere and anytime I want. So this is the limit as x approaches infinity, and I'll write it out one last time here, x over x plus 1 over x over x over x minus 2 over x. This is the limit as x approaches infinity of 1 plus 1 over x divided by, oops, what did I do there? This should be over x. Those mistakes creeping in always. X divided by x is 1, not this x, and then minus 2 over x. Now, what's a pretty important consideration there is that whether x is positive or negative infinity, both of these terms that I'm circling in blue would be approaching 0. So not only is the limit as x approaches infinity, it's a bad infinity, I got to redraw, that's going to drive me nuts. The limit as x approaches infinity of x plus 1 over x minus 2 equal to 0, the limit on the left is as well. And that is just that idea that when I approach zero inside a limit, it doesn't really matter if I'm taking the positive or the negative infinity of my variable, because 1 divided by negative infinity and 1 divided by positive infinity is 0 in both of those cases. And I wrote 0 here. Sorry about that, guys. What's going to happen to this limit is those 1 over x's are going to approach 0, and we have the limit as x approaches infinity of 1 over 1, which is actually equal to positive 1. It's a bad oversight, my bad. Now, what this graph looks like then, and again, we're going to talk more about concavity and a few other things. We know we have a vertical asymptote here at x equals 2, and we know we have a horizontal asymptote here, which is at y equals 1. We are going to talk much more about how to know where the function is, but in this particular case, my function looks roughly like this, where on the far left and the far right, we are approaching a value, y equals 1. And then as x approaches 2, my function has that asymptotic behavior. From the left, we can see that the function approaches positive infinity. Sorry, from the right, the function approaches positive infinity. And from the left, the function approaches negative infinity. It's a key kind of almost, a little bit of a shift between when you talk about horizontal versus vertical asymptotes. You do really have to try to make sure you stay within the descriptor or the technique for both of those things. All right, one more here, and it's got at least a little bit of that kind of initial setup that we force you to deal with, which is the idea that to find vertical asymptotes, I have to identify non-permissible values. So it's actually much better. I'm going to use function notation here to factor that denominator. Using difference of squares, I get x minus 2 and x plus 2. And that really lets me know that I have a vertical asymptote at x equals 2 and x equals negative 2. And then horizontal asymptote, probably somewhere, which is what we need to determine. So to figure out our horizontal asymptote, we're going to use the same technique that we ever had. And I'm going to do that one first. So I'll put it over here. I think I can fit both on one page here. The horizontal asymptote is the limit, and we'll deal with the positive first, as x approaches infinity, of x over x squared minus 4. Well, I'm going to multiply both the numerator and the denominator by 1 over x, as our normal technique would tell us to do. So the limit as x approaches infinity is now on 1 over x minus 4 over x. Well, 4 over x is going to go to 0. So we have the limit as x approaches infinity of 1 over x, which is equal to 0. Now, I want to kind of talk about that this expression right here, the limit as x approaches infinity or negative infinity is equal to 0. And I'll state that by writing the limit as x approaches negative infinity of 1 over x is also equal to 0. And I just want to put that means we have one horizontal asymptote at y equals 0. Now, what this means is there does not exist a value for x that will make that fraction equal to 0. And I would really, really encourage you to kind of check that. Pick different numbers for x, as large, as negative, as irrational as you want. It doesn't matter. There exists no real number that we can put in for x to get 0. And that's a really important consideration, that when we talk about those horizontal asymptotes, they are usually values the function never hits, although every now and again you can get that kind of special case where maybe we have a horizontal asymptote, and it's not this question, but you can have two horizontal asymptotes. And the function could, go above and then eventually approach it on the end. So it's really important that it's the value that in this case the function never reaches, but it can be a value that the function hits when x is equal to 4, but then approaches as x, approaches infinity or negative infinity. All right, to deal with our vertical asymptotes, we need to do 4 limits, and I'm sure you're thrilled about that. It's the limit as x approaches 2 from the left, the limit as x approaches 2 from the right, and then we're going to do the same thing for negative 2, but I'll do these two first. Now, because this is x over x squared minus 4, the limit as x approaches 2 from the left, we're looking at maybe 1.9. This is going to be a very small positive number divided by a positive number times, really importantly here, a very small positive value. And the reason why that positive value is small is as we approach 2 from the left, ooh, I messed up. I was doing 2 from the right in my head. That will be a small negative number. And I want to show how I know that. On your calculator, what you could put in is 1.9 squared minus 4. I know that 1.9, though, or 1.9 squared, sorry, is less than 4. So that would be a negative value. So a positive number divided by a small negative number gives me negative infinity. And I think I'm just going to do these limits in kind of a different color from now on. It's all bleeding together. So we'll do this one right, I promise. The limit as x approaches 2 from the positive of x over x squared minus 4 is a positive number divided by And I actually just kind of messed up my notation here. It's just not a good day, I suppose. But because I've left it as x squared minus 4, I can look at that as putting, 2.1 in there. Well, 2 squared is 4, so 2.1 squared is larger than 4. But it's not much larger. So we're going to have a very, very small positive number, which means that this goes to positive infinity. The last part then, it's looking at those limits as x approaches -2. This is going to be pretty similar. If you are stuck with this, please put in numbers like 2.1 or 1.9, or in this case, -2.1, and so on. So we're going to do the limit as x approaches -2 from the left, and the limit as x approaches -2 from the right of the same function. So x over x squared minus 4. This is also x over x squared minus 4. This is equal to, okay, really importantly, -2 from the left, you're looking at -2.1. Well, -2.1 is negative, so the numerator is negative. If I take -2.1 and I square it, I get a positive number slightly larger than 4. So this would be a small positive value, which means the function goes to negative infinity as we approach -2 from the left. As we approach -2 from the right, so -1.9, the numerator is still negative. But now my denominator would be a very, very small, in this case, let's think about it, and it's really important to go through it. -1.9 is approaching -2 from the right. So if I take -1.9 and I square it, I get a number slightly smaller than 4. So this is going to be a very small negative number, which means that this goes to positive infinity. Now, all of this can be summarized in a graph. Again, we are not worried about the middle behavior of the function. We are just talking about the behavior near the non-permissible values and the horizontal asymptote. So there is a vertical asymptote right here at x equals 2. There's another vertical asymptote, I'll try to space it at least reasonably well, over here at x equals -2. And then really importantly, there is a horizontal asymptote at y equals 0. So we have 3 asymptotes on this graph. Now, you can do a lot of extra stuff. This graph does actually go through the origin when x is 0, and that's a great example of, I said there was no value that this function makes it 0, and that is an oversight in my case. There is no value as x approaches infinity or negative infinity that makes this 0. But if I put 0 in for x, I get 0 over 0 minus 4, which is definitely 0. As we approach -2 from the left, it veers down to negative infinity. As we approach -2 from the right, it goes up to positive infinity. It has to go through that 0 point. And as we approach 2 from the left, it goes to negative infinity. Approaching 2 from the right is positive infinity. And then as x approaches infinity, the function approaches 0. This graph is certainly, checkable via your graphing calculator, but we do want to get to the point where we don't need that, and we can hopefully answer some of these questions just by using our limit techniques. All right, horizontal asymptotes are typically not fun for students, but once you get the habit of, dealing with those infinite limits, typically they do get a lot easier. Sorry about that weird kind of stretch there. Make sure you're trying these questions. Make sure that you're having problems. You're emailing me, and, we'll keep chipping away at this, and we'll get done the course before you know it. All right, good luck, guys. Email me if you need help.